and then we will ask a few questions. Okay? So only 20 minutes for all the papers.
Then, hello, ladies and gentlemen. I'm Emin Zur, a student in the High School of Communication in Tunisia, and I have the honor to present to you this presentation called Development of Indoor Localization Techniques. Let's see the contents of this presentation. Firstly, we'll begin by a short introduction concerning the wireless sensor networks and the indoor localization techniques before introducing our problematic. Then, the main problem is formulated and the tested solution for assuring the indoor localization are tested and studied in the next part. We will achieve finally by conclusion that summarize the significant obtained results and by a few perspectives that can be obtained. We begin by the first short of this presentation. You simply know that since the beginning of the era, the man wants to be located in any place. That's why the GPS were implemented to meet. However, the satellite cannot penetrate beyond the roof focal. This is unfortunate because it exists closed area large enough that we can get lost. For example, as we can see in this picture, the girl is lost in her university and asks her friend to help her find the room D27. This type of application is really needed in this indoor place, and system localization application will be already rectified. Then the GPS is imposed in the outdoor, but it is quite limited in the indoor. Indeed, the quality of signal is really deteriorated when the satellites and the receivers are not in light of sight. Also, the accuracy of outdoor and outdoor GPS it's about 5 to 6 meters, and for assuring the best indoor localization, we have to procure a precision not exceeding the few centimeters. Also, the signal process consumes the energy of the lifetime of the batteries, and this is not good for the receivers and the unreliable. Finally, the most important that the satellite signal cannot penetrate into the roof of closed area. That's why we need to find a solution that exploits the wireless sensor networks to localize the target and assuring a precision of a few centimeters. This is in this context that is based this presentation. To meet this purpose, we have to answer three main issues. Firstly, we have to exploit the wireless sensor networks and to define the constraints that have to be satisfied by our application and the means that will allow us to ensure the best localization satisfying these constraints. Now that the problematic is formulated, we can pass to the first section of this presentation, the wireless sensor networks and the indoor localization techniques. Wireless sensor networks is composed by a set of sensors that are connected to the sync and the task manager. These nodes are responsible for identifying and routing the information towards the collected points called also as sync that will transmit them to the task manager, which have the mission to analyze this information and make the decision necessary. The sample data it's being deployed following two methods. Firstly, it will be sent every periodic, every lapse of time. instance for assuring the real-time aspect of this application, and it will be sent after in grant of an event such as a certain chance of temperature or operation. For the indoor localization techniques, it exists many of indoor localization technologies such as vision or sonar technology. But in our application, we were interested in the radio wave technology. The shortwave technologies going from the Zigbee to the Wi-Fi are really suitable to be used into the building for assuring the accuracy of a few centimeters because of our application. For this application, we were interested in the Wi-Fi technology because our application is being developed to the Android device, and the suitable receivers exist at all the Android device or not device. Not to mention the fact that their access points can be deployed easily though at first we thought about the use of the Zigbee architecture, but we didn't use it because we don't have yet the suitable receivers at the Android device. And the Wi-Fi access ones have a probe and flow really higher than those of the Zigbee. Then that the main problem of this presentation is the introduction. We can explain the tested and deployed solution in this application. Firstly, we'll define the constraints and requirements that are to be satisfied. The most important is the accuracy, as I said before. It defines the error range obtained when we localize the person, and it have to be about a few centimeters to have the best solution. Second, we have the stability that is proper for the router. It represents the rate change of the RSSI values towards a fixed distance in the time. And finally, coverage radius that is still rather important because it can indicate us how far we can implement two routers with assuring the best localization without risk of interference. We can pass now to the first tested solution in this project, the fingerprinting. Fingerprinting consists of the creation of a table of the data table and database containing a set of reference points. For each reference point, we registered all about 1,000 value of RSSI of each router locates. Then, as the localization path, the application determines the router neighbors to the target device and calculates the least the least square error with each reference point. Then the target position will be matched to the points with which it has the minimum error. However, this solution isn't quite precise. And this, as we can see in this example, the x value that represents the real position of the target, and the closest reference points is indicated as you can see. Then this accuracy that demands our most conference isn't really satisfied, and to have best localization, we have to construct a huge database that is really exhaustive. Then this allows us to pass to the field of the triangulation. The next solution is the static localization. This method consists of the creating of a database containing the address, position, and the coverage radius of every router and service. Then, at the localization phase, the application will define the three closest routers, and the position of the zone localized target will be defined by the intersection of the three disks that defined by with whose center is still the position of each router, and the radius is the coverage radius. However, as you can see in the example, the the intersection of the three disks still a large zone. This is due to the fact that we use a static radius to localize the person. We have to minimize this intersection zone. For this, we have to determine a dynamic method that determines the relation and estimates the relation between the RSSI values and the distance separating each router and the target. This means as to the sound solution of this presentation, the course to find localization. This solution consists of three parts. Firstly, we will estimate the distance separating the router and the target. Then, they will at the location pass. They will extract the suitable equation and reducing the position of the tank by resolving this equation. We'll explain. To estimate the rotor position, we have to calibrate our rotors. For this, we registered about thousands value of RSSI for each distance, and we represent them as cloud counts as seen in this graphic. And for assessing the estimation of the distance in the RSSI, we use the trend chart that represents the best estimation that we have. This trend chart can be logarithmic, exponential, or linear one. But to deduce the best representation, we have a coefficient, resemblance coefficient, R square, that define the success of the resemblance between the estimated and the real values. For the routers that are tested, we find that the linear representative consists and represents the best estimates our results with resemblance coefficient about 90%. Then at the localization path, the application extract the parameters of this trend line and estimates the distance separating the target and the rotor. As you can see in this picture, the little green circle is indicating the position of the target. The zone of intersection of the three disks is minimized. This is our approach. It's better than the other solution. Also, for the application, we use now here we see three disks, but we use the intersection of three links. We have find these disks in thin links because the intersection of the three disks cannot really give us to count. But with the links, the probability of obtaining this intersection is quite important. Now that this solution is considered, we can pass to the third part of this application, when we will present the realization and implement of this solution on Android. Every solution detailed before were tested and implemented on Android device to determine the success rate, and we determined that the last one presented the success rate really important rather than the other. with an accuracy not exceeding the 2 or 3 centimeters. Then we implemented an application that calibrates the installed router and determines the parameters of the transfer. Then we had to implement an administrator part that manages all the routers to add, delete, etc. And an implement of a part that integrates the final solution and distributes them. We will give a few results about this application. For the administrative part, we saw an example for the adding fact. Also, as you can see, if you choose the add menu, we have just to touch the position disorder, and the dialog box will show to ask us to give the 3 parameters: the address, MAC address, and the parameters of the transducer A and B. And see the router is set as for the European parts that integrated this slide solutions. It was the estimation between the real position of the clearance and the estimated one. As you can see, the black circle, it indicated the estimated position of the data, and the X bias, it indicated the real position. As you can see in this example, the position is still the position is still really close to the real one. In this demonstration, we didn't find the real time aspect of this presentation, because when we tested we didn't have enough routers in our infrastructure. But if we have enough routers, we can be located at every step. To conclude, we have present in this project the wireless sensor networks and the technologies that are available in this world. Then we detailed the tested solution and deployed in this application that allows us to have the best solutions that for localization and satisfying the constraints required. And we have given given a few screenshots of detailing the application implemented. This project allows us to exploit the wireless sensor network fields and the indoor and outdoor locations that between that is such large and it can be open to few perspectives. Indeed, we can use this localization into three-dimensional places because the three-dimensional field is quite relevant nowadays, and many of the mobile devices integrated the three-dimensional frequency. Also, the mobile sensors field, it's a domain of research that remain recent and quite important. We can use this mobile to this field to ensure the best localization of the position. That we will have a set of fixed mobile and mobile fixed sensors and mobile sensors that will be displaced every place in order to cover all the place, all the indoor localization, and ensuring the best and minimizing the number of sensors used. That will be really efficient. Thank you for your attention. It will be easy to answer.
Thank you very much. And we hope that there is a few questions now. Any questions? No questions? Okay.
Merci pour votre présentation. Vous avez parlé au début de votre présentation des limites of GPS. Donc, des limites of GPS, quality of service, and energy consumption. Et vous avez mentionné les espaces fermés. Voilà, où on parle des limites de sécurité. Concernant votre présentation, donc la technique Wireless Sensitive Code, est-ce qu'elle a résolu, est-ce qu'elle peut résoudre cette loi limite ou bien nous allons résoudre seulement le troisième inconvénient de cette
Non, ça résout les trois parce que quand ils disent qu'un
vous n'avez pas, parce que vous n'avez pas parlé de la notion de consommation.
Oui, parce que bon, ouais, c'est vrai. Parce que quand on installe, quand le réseau capteur est installé, le traitement et traitement des données se fait au niveau local. Donc, quand on va traiter et transmettre les informations avec un routeur ou un point d'accès, la durée de vie ou la charge qu'on va utiliser elle est largement inférieure à celle transmise lorsqu'on se communique avec un satellite. C'est ça en fait le bon côté.
Elle est toujours en veille, c'est ça?
Oui, déjà, l'application elle est toujours en place. Elle va essayer. Et déjà, l'envoi des données à un point d'accès qui est proche. C'est mieux que d'envoyer un satellite ou de transmettre les données. Parce qu'il va y avoir un envoi périodique de données afin de permettre la localisation en temps réel. Si on envoie un routeur et si on fait le traitement nécessaire, ça va largement minimiser cette espace maintenant.
Merci pour votre présentation. Donc, normalement, la graph de state is distributed methods of optimization in the centralized network. And here, we are not first is decentralized.
Ce n'est pas centralisé, c'est distribué.
Distributed. So you didn't talk about combined sensors.
Bon, ça, en fait, c'est plus qu'une perspective. Ça représente en fait parce que le domaine du capteur mobile, il est en fait de distance. Si on peut utiliser, ce sera, si on va installer des routeurs X, et les capteurs mobiles vont être mobiles vont se déplacer selon la charge de ce endroit. Par exemple, dans cette hôtel. Nous allons installer des routeurs un peu partout. Le hall d'accord. Il sera, par exemple, hier, il était assez rempli. Alors, pour assurer la bonne localisation, les capteurs mobiles vont se déplacer dans le hall afin de pouvoir localiser tous les mobiles, tous les appareils Android, toutes les personnes. Ouais, les appareils Android, parce que les utilisateurs, pour utiliser cette application, doivent avoir Android. Donc, ça va se déplacer selon la charge de chaque endroit. Et ceci va nous permettre de minimiser le nombre de capteurs qu'on va utiliser. Parce que si on va utiliser que des routeurs fixes, on va devoir installer au niveau de son entrée environ 4 ou 5 routeurs. Et là, environ de chaque étage, on va créer le même. Alors sinon, on va installer, avec les capteurs mobiles, on va installer que 2 par routeur. Et les capteurs mobiles vont se déplacer entre eux. Bon, c'est juste une perspective que j'ai trouvée dans mon quelques recherches. En fait. Déjà, je connais un laboratoire qui effectue des recherches sur ce même sur ces capteurs mobiles pour assurer la localisation d'autres.
Le choix est fait parce que il y a généralement, si on cherche un admiral, ou des explications, j'ai pas de significatif pour l'organisation.
Justement, mais puisque l'Android, ça se trouve être assez répandu en ce moment et tout, donc il sera bien de mettre déjà même une extension, ça va peut-être intégrer au niveau d'iOS.
Une autre question aussi. Donc, comme pour faire une localisation, on a dit au moins pour la station de base. Les mobilités. Tout à l'heure, c'est le signal fixe. Il faut avoir un point pour voisin bien localisé, si vous voulez, pour qu'on réadapter le système de telle manière pour qu'il sache où il est en permanence. Et ça, c'est un terme de puissance de calcul, c'est pas bien. Je ne pensais pas mal de ça pour le faire. Une deuxième remarque par rapport à la réponse pour vous. Il y a deux types de localisation. Il y a quelque chose en localisation, il y a en positionnement. Ce n'est pas la même chose. Donc, dans la localisation, on a besoin d'énormément de recevoir, jusqu'à communiquer, etc. Dans le positionnement, c'est l'exemple du GPS. Je n'ai pas besoin d'envoyer un signal jusqu'à. Par contre, je reçois en personne, en permanence, du coup, je fais un positionnement. Ces deux termes-là, c'est très délicat à comprendre. Du coup, l'exemple, c'est-à-dire, quand je suis que en réception, je consomme l'énergie que le récepteur. D'accord? Que pour le récepteur. Ou 22 mAh, 17 mAh, c'est la même chose. Je n'ai pas besoin de calculateur pour venir ici. C'est pour ça aujourd'hui, pour l'outdoor, ça marche très bien, le GPS, l'outdoor, c'est très bien. Mais je n'ai pas besoin de signer. Dans votre cas, peut-être vous avez besoin, parce que bon, c'est très proche, quelques milliampères, enfin, regardez le faire, en plus, on prend des routeur, on pousse des routeurs et des systèmes, c'est très bien chouette. Dernière remarque, vous avez mis les aiguilles. Ça, c'est pas vrai. C'est pas vrai. Pourquoi? Parce que les aiguilles, aujourd'hui, consomment dans 10 milliampères, bon, peut-être vivent quelques jours, donc c'est différent de votre prix. Si vous avez une batterie de voiture, oui, peut-être. Mais ça ne dure pas longtemps. On a qui sincère, on n'a pas le droit de la autre question? Eh bien, il faut qu'on ramasse le papier. Je pense qu'il y a un responsable qui va ramasser le papier. Donc il faut noter. Merci beaucoup.